And so I gave this talk last year, but now with 1,000% more results and conclusions. So yes, this is the potential photochemical origins of banded iron formations. I'm Parker Castleberry at ASU. So first, banded iron formations. They're large sedimentary deposits of iron oxides. By large, I mean trillions of tons. These are, laser. These are very pretty ones in Western Australia, and they're alternating layers of high iron and low iron minerals. And they're thought to be formed by oxygen oxidizing iron in seawater that precipitates. And the thought for this comes from, if you look at oxygen levels in the atmosphere over time and BIF relative abundance, they correlate well. There's a lot of BIFs deposited right around the Great Oxidation Event. But there are some alternatives proposed. There's photoferrotrophy, which is a biological process. It's a type of anoxygenic photosynthesis that directly oxidizes iron. And experiments and modeling have shown that you could generate enough oxidized iron to make BIFs with this. And that is a beautiful lake where photoferrotrophy is studied. But there's another idea that is photooxidation. This is a completely abiotic process. And it's ultraviolet light turning iron 2 into iron 3. And this is a cartoon. I have somewhat abstracted mechanistic details. So you have an ultraviolet photon from the sun, hits an iron 2 species in seawater, turns it into iron hydroxide, and then that will precipitate, it's soluble, and then over time that is transformed into BIF minerals like hematite and magnetite. And the implication here is that, as I said, this is an abiotic process. So you don't need oxygen or even biological activity. So are these BIFs that we're seeing really signs of oxygen or life, or neither? So previous work has been done testing this. In 1983, Braderman et al. Used a mercury lamp. And they observed reactions using filters for long wavelengths over 400 nanometers. That's in the visible, not even in the UV. So that led them to believe that this iron species, FeOH plus, was responsible because it has absorbance going out to almost 450 nanometers. And this is important because, so this is the solar radiation spectrum, and here's the UV. So the Earth had no ozone back then, so it was somewhat proximate to this top of atmosphere spectrum there. And so if you have FeOH plus, it absorbs a huge region of the UV and getting into the visible where there's a lot more radiation. As one of my professors said, that's the meaty part of the solar spectrum. And Francois took these results, ran with them, and made an ocean model, calculated a mass accumulation rate. And he got about an order of magnitude more than an estimated natural rate for a BIF. So that led people to conclude this is plausible. But I went back to re-examine this. So I used a quartz reactor with ports for flowing gas in, venting, drawing samples, continuously purged with nitrogen CO2 gas, which 2% CO2 is not unreasonable for the Archean. And that's to keep oxygen out, because this is extremely sensitive to oxygen. Solution was deoxygenated DI water, sodium chloride, iron, and bicarbonate. So this is what I saw for 24 hours. And in the bottom there are those kind of orange precipitates. Raman spectroscopy identified those as lepidocrosite, which is consistent with the earlier work. So then though, well, the mercury lamp poorly matches the solar spectrum. It has all these peaks. And so I used a solar simulator as a light source, which is a xenon arc lamp and special filters to match the solar spectrum. But if FeOH plus is absorbing, then I should observe a reaction. So this is the dark control, no precipitation. This iron was measured on quadrupole ICP-MS, and everything was ratioed to sodium to correct for any evaporation, because these experiments took days. And dramatic pause, solar simulator also showed nothing. No reaction over 46 hours. This was quite puzzling, but the mercury lamp and the solar simulator have extremely different spectra. So there's just a few slight differences. So what I did is to test the wavelength dependence, which of these differences is important. I performed an experiment using the mercury lamp and light filters. It was one continuous experiment and periodically swapping out light filters. And so if I changed light filters and saw a reaction, oh, that's the wavelength that caused it. So to begin, I started with no light, dark control, and saw no iron precipitation. OK, good. And then light longer than 400 nanometers also showed no effect. This is different than what Konhauser observed, or not Konhauser, excuse me, Braderman. There's another paper, Konhauser, that does agree with this. So. And then light longer than 345 nanometers also showed no effect. So that is getting down into the UV. And then, boom, 295 to 345 nanometers caused significant iron precipitation in a couple days. And then the full spectrum didn't actually show an increased rate. So I can conclude, oh, and precipitation stopped when the light was turned off, just to make sure. So I can conclude that mid-UV, so 345 nanometers or so, is what's causing this reaction. And then, so what I did is using this new wavelength dependence that I found, I went back to the old models, recalculated it using only that region that I observed and not the long wavelength where you have all of the higher solar radiation. And I calculated rates that are 6 to 54 milligrams of iron per square centimeter per year, depending on the concentration of iron 2. There's a lot of uncertainties and assumptions that went into this, but that's just to get kind of a rough estimate. And like I said, I'm missing the longer wave absorbance here. So this is 5 times less than previous models, 5 times slower. But it actually still compares favorably to estimated natural rates. But looking at, I talked about those alternative theories like photoferrotrophy. Photoferrotrophy, there's actually, you could get numbers of around 500 milligrams per square centimeter per year for similar iron concentrations. So I can conclude here that I reevaluated iron photooxidation and found it sensitive to wavelengths between 295 and 345 nanometers. It results in photooxidation rates 5 to 6 times slower for a predicted model. And so if photoferrotrophy was around, or like oxygen from oxygenic photosynthesis, that would likely outpace this process. But this still is possible in the absence of any biology at all. So questions? Actually, I have some time, so I can talk a little bit about future work. I said I had dissolved carbonate in there. Another thing, I've been wanting to test different additives to this, things that could have redox interactions with the iron. Also the effects of dissolved organic carbon, because I could see a photoreduction, which is what happens a lot in modern systems. So I might actually get some filtered seawater and do experiments with that. And then after this, there's other things I could look at photochemical-wise. So, OK, thank you. And I do have time for questions.
OK, didn't even have to ask.
So I had a question about your relative xenon arc lamp and
Yes.
mercury. So, I mean, xenon arc lamps have a lot of output in that same near UV range that you're looking at. So, what is the wattage of your various lamps? Like, is it just coming from a difference there? Because if you look at the spectra, your xenon arc lamp had much less just total output.
Referring to here?
Yeah.
Yeah. The wattage, it was 300 watts.
Okay. I mean,
So.
I guess my question is, the xenon arc lamps, have a lot of energy in that range too. So maybe it's just a power issue with why you weren't seeing it.
It's a power issue. I have ideas that the air mass filter that I put on this, because that corrects for more of the longer wavelengths that I was originally thinking might be interesting. Is actually having some absorbance right in this region, cutting down on the xenon arc spectrum. So essentially, the air mass filter for a solar simulator might not actually be the best solar simulator for these UV wavelengths. But yeah, I'm thinking about doing that. Also talked about getting a deuterium arc lamp for a, I guess, consistent UV spectrum, longer wave, or shorter wave. But yes.
I was wondering, so the solar spectrum that you're showing here, is this for a quiescent sun or like a flaring sun?
Or this is my solar simulator.
Right. But it's supposed to simulate a quiescent
Yes.
sun. OK. I guess I'm just wondering, since the sun does have
Yes. Evolution.
cycles. Yeah.
That is one of my favorite questions. There we go. So here is the evolution of the solar spectrum. And while the solar simulator didn't take this into account, I actually took this into account in my models, but the sun was 20, 25, 30% fainter early in its history. So this is photon flux, and the black is the modern spectrum, and then these are different ages for the sun. So 100 million years, 700 million years, and 2 billion years old. And the interesting thing is that, because I heard a lot of theories, well, the sun was brighter in the UV. But actually, that is true, but only for wavelengths under 200 nanometers, which aren't of interest for this reaction. So they're generated by different processes. So did that answer your question, really? Or?
I think I'm referring more to the solar cycle, so the magnetic cycle,
I see.
How you get more flaring activity.
It's an average, really.
Okay.
More questions?
So given the timing of BIF deposits that we see in the rock record, how much of a contribution do you think this photooxidation had on those formation of real-world deposits?
Right. Actually, let me go to As I scroll back through all my slides. Yeah. So, I mean, what I think is entirely possible is that things like older BIFs here were deposited by photochemistry, and then if at some point photoferrotrophy evolved or axogenic photosynthesis, then that is what caused this huge increase. So there might be some background of photochemistry, and then on top of that, a large biogenic signal.
Okay, I am not at all very familiar with photochemistry, so I have a very basic question for you.
Yes.
In the photooxidation of the reduced iron, where's the oxygen coming from?
So you're saying
Is it like dissolved carbonate?
that oxygen?
Yeah.
That oxygen comes from water, actually.
Okay.
The oxidized iron takes a nearby water molecule and is like, give me your OH.
Yeah, gotcha. Cool. Thanks.
Okay, do we have any more questions?
So since the OH comes from the water, don't you get a buildup of hydrogen gas that's reducing?
Well, you get hydrogen gas, yes. But actually, this is in the ocean, and it actually escapes and goes into the atmosphere.
So in your setup, it's not an ocean; it's smaller. So what do you do with the hydrogen that's?
Well, I'm
bubbling out?
continuously flowing gas through my experiment.
Oh, so there's an in and out.
Yes.
Oh, okay.
In fact, I didn't talk about it, but I didn't talk about a gas flow rate, but I'm actually at 500 milliliters per minute. I have a huge dewar of liquid nitrogen to keep this experiment going.
Okay.
I have tried lower flow rates, but oxygen actually diffuses in. Because I calculated a few ppm oxygen will give me oxidation rates that I observed with the lights.
Okay, one last question.
So just maybe this may be another geological question along with. So due to the fact, I guess, there's a certain period of time where parts of the Rocky Mountains were actually underwater. So is this actually how we're getting the bands on certain rock formations that are on land today? Or?
I'm not sure about on land today, but I mean, yeah, I'm not sure about modern systems, really.
Okay, let's thank Parker one more time.
Cool.